The Moon, our closest celestial companion, our indispensable dance partner through the cosmos, lighting our night sky and gently tugging at our shores. Few have walked on her surface, but her allure remains strong. Once again, we are glancing her way with renewed interest and with a view to returning very soon.
Houston, Tranquility Base here. The Eagle has landed. Roger.
When I was a little girl and people were always asking me, what do you want to be when you grow up? And I used to always go, I want to work up there. As an engineer, you dream of a job like this where you get to follow in the footsteps of some of your childhood heroes. And of course, for me, the Apollo missions, seeing these folks on TV step on the moon and work for NASA, as an engineer, it's just a dream to be able to say, you know, I want to do that too, and here I am.
Only a dozen Americans have kicked the dirt on the lunar surface. It was a bold and dangerous engineering achievement driven by a political agenda.
The Apollo program was important because it showed that we could leave our home planet and visit an object like the moon. However, what we want to do next is learn how to live and work off of our home planet on another planetary surface, like the moon. By developing this capability, we'll be able to know how to go throughout the inner solar system, which has many important destinations, both for science understanding and also may have economic importance for not only our generation, but for future generations.
The Soviet Union and the US had peppered the lunar surface with soft and hard landing spacecraft. The Soviets' Luna 24 was the last of that program, returning soil samples that contained traces of water. Much of science and technology has advanced since the 1970s. The mechanism of world politics has evolved, new partnerships have formed, new players are looking skyward, and more recently, private enterprise has taken up the challenge. With the faintest of inklings that there may be usable water on the moon, a forensic focus has turned to the southern polar region. Scientific programs in the 90s refocused on the moon. Japan was the first to revive lunar research and only the third nation to achieve lunar orbit with Hi-10 on a dust-collecting mission. The US followed with Clementine, a joint NASA military project. It completed a mapping survey of the lunar surface along with gravitational data and evidential proof of possible water ice hidden in a south polar crater in permanent darkness. 4 years later, Lunar Prospector mapped lunar resources, gravity and magnetic fields. It was also impacted into the southern region of the surface to elicit more evidence of water ice hidden in the craters. Europe's contribution to this resurgence in lunar exploration began with the launch of Smart 1. This tiny, ion-propelled satellite catalogued key chemical elements on the surface. It also enhanced the theory that the moon was the result of a collision between Earth and a smaller celestial body called Theas some 4.5 billion years ago. Japan's second probe was Selene, better known in Japan as Kaguya. It continued extensive observations of the lunar crust and also carried the first high-definition cameras into lunar orbit, giving us a clearer picture of the rugged surface. Another proof of capability this time by India. It also carried a NASA mineralogy mapper and an impact probe. It played a key role in the confirmation of water hidden in the southern lunar pole. 8 months later, NASA launched the Lunar Reconnaissance Orbiter, or LRO. It has spent the last few years mapping and scanning the lunar world with sophisticated sensors and continues to return a wealth of data.
The Lunar Reconnaissance Orbiter is, as its namesake says, a reconnaissance mission to the moon. Our job is to take a suite of very powerful scientific instruments and make an atlas of the entire moon, in some places in very great detail. Topography, mountain heights, mineralogy, temperatures, abundances of resources, including potentially the intriguing possibility that there's water at the moon. We put all this together into a data set by flying low over the moon for a year. This is the data that the people designing the human systems, designing the systems, picking the sites, need to take us back to the moon.
This robotic mission commenced operations in June 2009. It was hoped the suite of sensors would fulfill several scientific goals, not only for the moon, but as a framework for understanding planetary processes throughout the solar system.
The LRO instrument suite is comprised of 6 instruments and 1 technology demonstrator. And they are geared towards providing us a variety of data sets ranging from a thermal map of the moon, global topography, and most importantly, looking for resources like water ice on the moon. The entire suite should provide more of an atlas as opposed to a map, so that we know where to go on the moon, where to have the safe landing sites, and where to put things like lunar outposts in the hopes of having human exploration in the near future.
The data being returned from LRO and the other probes draws a clear image of the evolution of the lunar surface and why it is composed of exactly the same elements as the Earth. After coalescing from the Earth-Theas collision, the proto-moon cooled, then suffered several major collisions from orbital debris, which created many of the largest surface characteristics, including the mares. Cratering continued relentlessly over the millennia, drawing the familiar lunar vista.
My name is Lynn Carter. I'm a research space scientist, and I work with the Planetary Geodynamics group here at Goddard. I study the geology of planetary surfaces, the Earth, Moon, Mars, Venus. There's a lot of things you can learn about the Earth by studying other planets. For example, on the Earth, we have a lot of erosive processes. You know, it rains, it washes parts of the surface away. We have plate tectonics, which recycles the crust. But on other planets, those processes don't necessarily occur. So, for example, when we look at the Moon, we're seeing a surface that's much older. We can use impact cratering on the Moon to sort of understand how many impacts happened, the size of the objects that were hitting each other in the early solar system. One of my favorite things is to use radar remote sensing. For example, on Mars, we can use radars to sound all the way to the bottom of Mars polar caps and see all this layering within the polar caps. And on the Moon, we're using it to study impact cratering. Sometimes when an impact crater is formed, a huge sheet of melt is thrown out. This melted rock flows across the surface, but then over time, it's covered over by stuff from other impacts. But with the radar, it just blows right through all of that, and you can see this beautiful image of the melt flow coming out of the crater.
Launched with LRO was LCROSS, or Lunar Crater Observation and Sensing Satellite. It deployed sometime later than LRO and had a finite mission. LCROSS and the rocket stage that delivered it were deliberately crashed into the craters of the South Pole, whilst LRO orbited above and observed the impacts. The debris and gases thrown up from the lunar surface were closely studied by LCROSS as it too descended to the surface. The missions found evidence that the lunar soil within these shadowy craters is rich in useful materials. The Moon is chemically active and has a water cycle. Scientists also confirmed the water was in the form of mostly pure ice crystals, which had not seen sunlight for billions of years. LRO has continued to operate in polar orbit, making observations of the South Pole, And with repeated flyovers, it has drawn up a detailed map of neutron densities in the region, revealing where hydrogen and thus water can be found within the lunar soil. The importance of this discovery cannot be overestimated. Having this resource in situ means independence from the cost and effort of bringing water from Earth to the Moon. It can be used for creating rocket fuel, oxygen to breathe, water to consume and to irrigate crops, and used in other processes to manufacture building materials from the lunar soil. Launched in 2007, NASA's 5 Themis spacecraft have now successfully completed their 2-year mission to determine the cause of geomagnetic substorms. Because they are continuing to work perfectly, NASA redirected the outermost 2 spacecraft to the Moon. This new mission was called Artemis, and they studied the magnetospheric environment near the Moon. They also observed the effects of surface electric fields and ions from the solar winds on the lunar surface, and determined the internal structure of the Moon from variations in its magnetic field.
Well, in a nutshell, what we're finding is that the polar craters are very unusual electrical environments. Well, the solar wind is actually a relatively tenuous gas that's emitted from the sun, but it's not a neutral gas like the gas in this room. It's actually a gas that's really, for the most part, free ions and free electrons. So as you pass by, for example, a polar crater, the electrons will actually fill into the crater ahead of the ions. Now, as it turns out, as it does that, you create an electric field. It's called an ambipolar electric field, and that electric field then drives in the ions.
These hidden troves of water ice and other volatiles in the polar craters may be protected by a dangerous electric charge of hundreds of volts.
Three, 2, 1, 0, and liftoff of the Delta II with Grail. Journey to the center of the Moon.
Grail consisted of 2 probes called Ebb and Flow. Linked together in a single flight path, they studied the gravitational field of the Moon, generating maps like this crustal thickness atlas. It reveals much about the interior of the Moon and even has some surprises.
2 years ago, we reported evidence that the Moon is shrinking. Now we've found evidence that the Moon is actually being pulled apart, forming features called graben. So the shrinking Moon, it turns out, is not shrinking everywhere. Some places the Moon is actually expanding by a little bit. So finding these young graben was a real surprise, because we thought, well, all these lobate scarps are telling us the Moon is shrinking. So what are these little small graben that are telling us the Moon is pulling apart doing in this picture? How does this all fit together? All that's related to how the Moon has evolved, how the Moon has lost heat over its 4.5 billion year history. Most of the terrestrial planets, when they formed, were very hot, and they got so hot that they actually completely melted. When that happens, they will be in a general state of contraction because they're still hot on the inside and cooling down, and as they cool, they want to shrink. Only the outer part of the Moon melted, forming what is called a magma ocean. And in that model, the balance of stresses or forces that are acting on the Moon would allow us to form both these small lobate scarps that show contraction, as well as these small graben that show the Moon being pulled apart. One of the really, really exciting returns of the Lunar Reconnaissance Orbiter mission is that we've seen this now growing evidence of very young geologic activity on the Moon.
The Moon's crust is much thinner on the near side, 68 kilometers thick on average, and varies from less than a kilometer under Mare Crisium to 107 kilometers thick just north of the crater Korolev on the lunar far side. The Moon's mantle is only partially molten, and the Moon's center of mass is offset by about 2 kilometers in the direction toward the Earth. This and other data quickly changed our understanding of the moon. To gather more evidence on the unusual electrical properties on the lunar surface and how it affects lunar dust, NASA sent LADEE, the Lunar Atmosphere and Dust Environment Explorer, to investigate.
At higher altitudes, we saw very few dust particle impacts, but the lower we went with LADEE, the more we saw, and it's a very, very steep rise. So if you're operating with spacecraft very close to the surface of the moon, as you would with a robotic lander or a human lander, you might need to consider the fact that you've got more dust there in the way as you come in.
This probe flew progressively lower and finally impacted on the surface.
Ignition, throttle up, main stage. Yes, sir.
This is Morpheus, a robotic self-guided lander. You tell it where to land and it will do the rest, independently seeking the safest course and avoiding any rocky dangers. The ESA were also developing an autonomous lander to perform the same function.
The lunar lander is a small but very challenging mission. The most important part of it is, of course, landing on the south pole of the moon, which requires innovative solution concerning landing, hazard avoidance, navigation, and in fact, this is the mission which will bring about the new generation of navigation and guidance sensor, algorithm, and software.
But a fiscal year is a long time in space. NASA now have little interest in returning men to the moon. They are firmly focused on a Martian landscape. The Europeans have had budget cuts. The ESA lander now shelved for the time being. This leaves the door wide open for Russia and the younger players, China, India and Japan, plus several private companies now developing the same technology to put first robots, then humans on the moon. All this time, the Chinese National Space Administration, or CNSA, had launched 2 orbiter reconnaissance satellites, Chang'e 1 and 2. Then Chang'e 3 deposited a lunar rover on the surface. Their latest, Chang'e 5, made a return trip around the moon. They are firmly set on a permanent manned lunar base.
I think the reason this has resonated with so many people and all over the world, it's not just our country, is because everyone can look up in the sky and see the moon. And I think a lot of people remember the Apollo landings, the first, man on the moon, and you can also look up at the sky, and I believe that people, it's very tangible to them that way. The moon, they can relate, and so they want to be a part of it. That's my theory on why people are just so connected.
The moon is indeed a tantalizing prize. The Chinese have their lander and rover there now. Japan and India will be next. South Korea has an interest along with Russia, Canada, France, Italy and the United Kingdom. Private enterprise has had a prod with the Google Lunar X prize. The $30 million prize pales beside the glory of being the first private company to land a robot on the moon and to explore at least 500 meters and transmit high-definition images back to Earth. So far, there are 4 hot contenders. The Barcelona Moon Team, a consortium of companies headed by Galactic Suite Design. Their interests lie in space technology and industry with a strong focus on tourism. Penn State Lunar Lion Team. Faculty and students are developing a spacecraft to land on the moon, then lift off again and relocate to fulfill the prize requirements. Moon Express is a group of space and Silicon Valley entrepreneurs looking to mine the moon for its valuable resources like platinum, titanium, and the rare isotope helium-3. Finally, Astrobotic Technology, a Pennsylvania-based company with support from other companies including Alcoa and Caterpillar. They have already reserved a launch on a SpaceX Falcon 9 launch vehicle. Getting to the moon is one thing, staying there is another.
It was
one thing to go for a handful of days in Apollo, and go when you knew that the sun was quiet, or you hoped the sun stayed quiet, and you took the risk, you calculated the risk of cancer and such, and you made a short mission. If you're going to live there longer, you need to understand it well enough to go, here's what I need to do to protect myself.
One of the things that we're looking for in the LRO mission is how the high radiation environment affects our ability to explore. So if we bring cameras or communication devices, how will they be impacted by the cosmic radiation? We need to protect our equipment as well as ourselves.
We want to be able to go back to the moon so that we can live there for long periods and work on the moon. So we need a mission that can help us find the best places to go and determine how to go back there safely.
Access to solar power continuously, that may be the first and most important reason over the near term. And then the possibility of resources being there. Those may take much longer time before we're able to really exploit those, but the solar power is something we can exploit right away.
Whether it's water ice to have water, or potential minerals that we could use as raw materials to make into things that we would need.
All the major players have designed and planned many varieties of lunar bases. NASA, ESA and private contractors have concepts on the drawing board. As more information comes in from the lunar satellites on the environment, resources and dangers of cosmic radiation, these plans evolve. One of the latest is to use 3D printing technology. With all the challenges and difficulties, many have made firm commitments to establishing bases within 10 to 15 years. Some for scientific research, others for commercialization and tourism. Some would choose not to send test pilots and scientists, but stewardesses and sommeliers.
When we look back on what we did in LRO and we look at what followed, I think we'll see a profound impact. We'll see us as really being the small first step where we have human beings permanently off this planet, beginning to move out into the solar system, starting with the moon. As that pans out, I think we'll be a small piece of a profound development that when history looks back, say this time we went back to the moon, this time we stayed, and we moved on from there.
As we continue to study the moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments and new technologies, we will continue to improve our knowledge of the moon and better understand the history of our solar system.